Okay, so now let's talk about solution stoichiometry, specifically aqueous solution stoichiometry. So we're concerned with reactions in which the solvent is water. We can describe reactions in solution by writing one of three types of equations. So the first is molecular equations, those are the most complete. The second is ionic equations, which separate all of the ionic compounds into their component ions. And the third is the net ionic equations. So, net ionic equations leave out the so called spectator ions. And when we're dealing with reactions of ionic compounds, not all of the species involved in the reaction necessarily react. Some are spectator ions. They're just along for the ride. They're not actually engaging in any of the interesting chemistry of the reaction. So net ionic equations leave out the spectators and just focus on the ions that are really involved in the chemistry of the reaction. Okay, so that's three types of ways that we can describe reactions by writing three different types of equations. But there are also three types of reactions in solution chemistry. And this video is just going to focus on the first one, but I'm just going to tell you that the three types of reactions in solution chemistry are precipitation reactions, which produce a solid, acid-base reactions, where an acid reacts with a base, and redox reactions, which is short for reduction oxidation or oxidation reduction reactions, in which electrons are transferred. I'm going to have at least one video devoted to each of those. And this video is going to be devoted to the first type, which are precipitation reactions. Precipitation reactions are reactions in which we produce a solid. So an insoluble solid, we call the solid a precipitate, is produced from a solution. And when we mix certain species together, combining solutions of different types of salts, depending on how their component ions interact, you can get a solid to form. What you will see in the laboratory is a cloudiness appearing in your flask. And that cloudiness is really particles of solid that are crashing out of solution, that are precipitating from solution. So an example is if you take two solutions of potassium iodide and lead 2 nitrate, and you mix those two solutions together, a precipitate of lead 2 iodide will come out of that solution. So let's first practice by writing molecular, ionic, and net ionic equations to describe that precipitation reaction. So what we want to do is we're basically translating these words into a chemical equation. So we need to take the potassium iodide. It's in solution, so we want to say that it's aqueous, and we want to add it to lead 2 nitrate. I'm going to leave space in front of lead 2 nitrate in case I need to balance the equation with a stoichiometric coefficient. So these are two solutions. They're both going to be aqueous. When they come together, the question tells me that we're producing a lead 2 iodide precipitate. So that means that I am making, oops, I forgot my B in lead. That means that I am making a lead 2 iodide solid, a PbI2 solid. Okay, let me fix my handwriting there a little bit so there's no confusion. PbI2, solid. It's implied that the potassium and the nitrate aren't doing anything. So I'm just going to write KNO3, the other counter ions, assuming that they're together. And I know that K has a +1 charge and nitrate has a -1 charge. So that means that they're going to come together in a 1-to-1 ratio. So I can write it like this, KNO3. Since it didn't mention anything about them being a solid, I'm going to assume that they are still just in aqueous solution. So this would be how I would write the unbalanced precipitation reaction for that process. Now let's balance it. Okay, first thing I notice is that I need to have two iodines on the left. So putting a 2 there brings my iodines into balance, but it throws the potassiums out of balance. So let me put a 2 here. And then that looks pretty good because now I have two nitrates, one on each side. Two nitrates on each side, two potassiums on each side, two iodides on each side, and one lead on each side. So it looks to me like everything is imbalanced. So this would be my balanced molecular equation. This is that first type of equation. I'm going to call it A for the molecular equation. In the ionic equation, what you do is you pull all of the aqueous species apart into ions. Okay, so for the next step, to write the ionic equation, you take all of the aqueous species and you pull them apart, pull apart the aqueous species into their component ions. So everything except the lead 2 iodide solid is going to be pulled apart in this example. So this is B for the net ionic equation. And I can use the balance that I have up here. So looking up here at the K Ki, I have 2 potassium ions and 2 iodide ions. Okay, so I just pulled those apart into their component ions. I also am going to have a lead 2 plus ion. Okay, all of these are aqueous species, and now 2 nitrate ions. So I'm keeping the balance of the reaction by keeping the number of ions consistent with what it was in the molecular equation. Okay, ionic equations tend to be really long, so for the products, I'm going to go on to the second line. Now this, the solid stays intact. I don't pull the solid apart into ions because the solid is still a solid. It's not an aqueous species. So that's what's crashing out of the solution here. And then finally, I have 2 potassiums and 2 nitrates. So once I finish writing down all of the ions involved in my ionic equation, I should make sure it's balanced. So 2 potassiums on the left, 2 potassiums on the right, 2 iodides on the left, 2 iodines in the solid on the right, 1 lead on each side, and 2 nitrates on each side. So I'm good. This is my ionic equation. Now, I want you to notice something about this ionic equation. We have certain species that are the same on both sides, and species that are the same on both the products and the reactants side of the reaction. These are called spectator ions. Nothing is happening to them over the course of the reaction. They are the same on both sides. So I can leave them out, basically cancel them out to write to get the net ionic equation. So the net equation, so leave them out to get the net ionic equation. So the net equation is just going to be, let's see, I'm going to cancel out the ions that are the same on both sides of the reaction. And I'm going to be left with, I'm going to reverse the order just to make it a little prettier. Lead 2 plus coming together with 2 I minuses to make the PbI2 solid. Okay, so this would be the net ionic equation. The net ionic equation focuses in on the action. The action is where I have the lead ions and the iodide ions coming together to make the solid. So this would be the net ionic equation for that precipitation reaction, and it leaves out the spectator ions. So we can use this kind of information to do some stoichiometric calculations as well. So you're going to see several problems in your homework where you have to both write down equations and then do some math. For example, what volume of 2 molar sodium chloride should be added to a silver nitrate solution to produce 10 grams of silver chloride? So you have to make a lot of inferences here. And one of the inferences that you have to make is that it'll actually help you always to write the chemical reaction. So always, always, always write down the chemical reaction. I'm adding sodium chloride, a solution of it, so it's aqueous, to silver nitrate solution, so that's also aqueous. And the problem is telling me that I'm producing 10 grams of silver chloride. So that is implying that I am making a solid. Okay. The other implication here is that the sodium and the nitrate are just spectator ions. So I'm going to add those in as spectators here, as aqueous ions. So this would be the reaction that I would write down if I translate that problem into a chemical equation. I just wrote it as a molecular equation here. Is it balanced? Yeah, it looks like this one just so happens to be balanced the way I wrote it. Now, once I have the balanced chemical equation, then I'm ready to do the math. Then I'm ready to do the stoichiometry calculation. So I want to make 10 grams of silver chloride. So let's convert that into moles, and then that should give me a good starting point to figure out the rest of this problem. So 10 grams of silver chloride, I'm going to convert that into moles by using the reciprocal of its molecular weight. So the molecular weight of silver chloride is about 143 grams per mole. Now, looking at that balanced equation, I have a one-to-one relationship of sodium chloride to silver chloride. Okay, just looking at that balanced equation, there's 1 mole of silver chloride produced for every mole of sodium chloride. Okay, I get that from the stoichiometry of the equation. So now I've set it up in a way that enables me to cancel out the grams and the moles of silver chloride. And now I can use the molarity of that silver chloride solution to figure out the volume. I'm going to use the reciprocal of that molarity. I have 2 moles of silver chloride, sodium chloride rather, per liter. And that is the final piece that enables me to cancel out the moles of sodium chloride to get the volume of sodium chloride. So I can answer my question as to what volume of sodium chloride solution I need. So it should give you something like 0.0348 or thereabouts. All right, so when you have to do a stoichiometric problem, you should always, always, always write the balanced reaction first. That is key.